Hi, everyone, and welcome to Full Device EMC Simulation, including printed circuit boards, enclosures, and cables, an EMA Expo 2025 event. My name is Sophia Habibi, and I'll be your host for today's presentation. Please use the Teams webinar Q&A feature to submit any questions you have during the webinar. After the presentation, we'll address any submitted questions. Should there be any unanswered questions at the end of the webinar, we'll address them via email. Our speakers today are Sebastian Soldwish and Ryan French. Sebastian is a senior scientist and product manager at EMA with a background in engineering physics from the Colorado School of Mines. Over the past 6 years, he's tackled complex electromagnetic challenges across aerospace, defense, automotive, and high-tech industries. He's led multiple R&D projects for the Navy and now drives innovation in EMA's EMC and ESD simulation tools. Ryan is a signal integrity engineer specializing in PCBA design. With a master's in physics and a background in commercial aerospace, he brings valuable experience in SI EMC analysis to EMA, where he's helping expand our capabilities in board-level simulation and design. To kick things off, I give you Sebastian.
Hi, everyone. Excited to talk today. As Sophia said, my name is Sebastian Soldwish, Senior Scientist and Product Manager. Today we'll be going over quite a bit, but first wanted to start with a little bit of background on EMA and our tools at a high level. I'm sure many of you are already familiar with, in general, what EMA does, but I think an overview of our general capabilities is some great context for going forward. So overall, we got our start as consulting for the aerospace and defense industry way back in the 70s. And throughout that time, we developed our expertise in many type of electromagnetic phenomena and built these internal tools that after our partnership with ANSYS in 2019, we were able to commercialize and build our tools, ANSYS Charge Plus and ANSYS EMC Plus. Really, overall, what the consulting services has really helped us in the development of these tools is we're not just building our EMC Plus and Charge Plus for our customers. We use them every day. It gives us a good pulse on the focus of industries across the world and helps us leverage our expertise on solving real problems and implementing features that are needed to solve such problems in our software. Beyond that, we also have our expertise in measurement, which lends well into having a great pipeline for our software validation. Overall, we have many capabilities for solving EMI, EMC from everything crosstalk, radiated emissions, susceptibility, conducted emissions, conducted susceptibility, ESD, many different radio frequency applications, spacecraft charging, lightning, radiation effects, and so on. For our software products as a whole, we have ANSYS EMC Plus on the left. This is going to be our tool that we're going to be focusing on today. This is a platform level electromagnetic modeling tool. Its basis is a finite difference time domain solver hybridized with a multi-conductor transmission line solver. We use this for solving everything from individual PCBs up to entire aircraft or cars with thousands of cables and harnesses in it. On the right is ANSYS Charge Plus. This is our multi-physics solver. This has many different capabilities from spacecraft radiation hardening, semiconductor industry, but the one that we're going to be touching on a little bit today is the ability to simulate electrostatic discharge events. In the case today from like ESD guns. So today we're going to talk really more about full platform simulations in electronics. So we're talking enclosure, cables, and PCB together. In general, one of the big things that gets our customers interested in this product is the high level of complexity that we're able to include in a single simulation. And so uh, with that, I wanted to make sure that we're able to spread the word on like how we are extracting our engineering insights out of these simulations. What can we simulate? How do we simulate? And when do we make our judgments? What is our goal with simulation? Like I said, many new customers come with the motivation to solve a specific certification issue. This might be failed radiated emissions or conducted susceptibility immunity for their platform and in the past, and they want to know if what changes they need to make to their current platform, or is their new platform going to be able to pass certification when they go into the chamber that might have taken months to schedule and have to bring in dozens of engineers in just to finish out this measurement. And so if you're able to know how you're going to perform in these certification events, then you're able to save quite a bit of timeline, money, and improve performance of your overall platform. However, replicating your test environment is an excellent goal, but will not happen overnight. A lot of customers, they want begin an interest in the simulation process when a problem has already arrived, and that is a great motivator. But being able to make a one-to-one model of your platform in a very short amount of time is generally not possible. However, today I want to go over how we can get engineering insight out of your model as you are building it up in complexity. This one enables a fast response to any problems that might arise, but then also helps reinforce good design practices if you are implementing your simulation at the beginning of your design process. Overall, it's better to be proactive than reactive across all things in engineering. And I think that is well understood across many industries. So to go through this, we're going to go through kind of this theoretical case study. Ryan French on the call will be taking over towards the end of this presentation, but he made a custom microcontroller platform, many different ICs and applications for this. It's going to perform basically like a Arduino. We plan to continue and on these models that we'll be showing today and eventually go through some full validations of this platform since we own the IP for it. So for the step-by-step, we're going to start with just an enclosure simulation. And this will be running a shielding effectiveness workflow. We'll talk about how this can help you solve emissions and immunity problems before you even have any information about the internals of your platform ready. Second, we'll add a little bit of complexity. We'll have a simplified representation of the board, but we're just focusing on enclosure plus the cables together and talk about how we can start to get a little bit more complexity, have a little bit more insight on emissions and immunity performance before we even have our PCB information in here. Then finally, Ryan will take over and talk about all of the different performance indicators we can extract from PCB only simulations, and then we'll combine all of these portions together into one full platform simulation. Starting off with the enclosures. So here we have a metallic enclosure made for that custom microprocessor board, has several connector ports, apertures, that for HDMI, USB-C, power in, Ethernet, and an SD card. For this first simulation, we're just going to impinge a plane wave driven by a Gaussian source and measure the fields on the interior of the box to extract shielding effectiveness. This simulation, we're going to mesh with a 0.5 millimeter mesh size. This is able to mesh in less than a minute, and our overall computational domain has about 8.3 million elements, and we're going to resolve 50 megahertz to 60 gigahertz for the shielding effectiveness extraction. Simulation time is about 20 minutes on a desktop with a 4090 NVIDIA GPU. So just taking a look at these initial results, we see that we have decent shielding effectiveness at low frequencies, but then it rapidly drops over 1 gigahertz, and then at about 7 gigahertz, we have virtually no shielding at all. Our apertures are dominating the response once we get into those high frequencies. So we want to think, what are our options to improve performance? What features of the box do we need to preserve? So our goal for this enclosure only simulation is let's try to improve our shielding effectiveness up to 10 gigahertz without sacrificing our enclosure's thermal performance, manufacturability, form factor, to help improve our emissions and immunity performance. We'll try to optimizing shielding effectiveness performance is generally a very elegant and cost-effective way to improve emissions and immunity, and even might not require a lot of complexity in your understanding of maybe some different EMC, EMI requirements. The can just modify your CAD mesh and hit run a lot of times, and we have some different automatic shielding effectiveness workflows that can be leveraged for simulations like this. So first, what is the root cause of our performance here? Really, in this case, it's hole apertures, HOLE. When the wavelength of our fields become closer to the size of our aperture, they can transmit through much more readily. And so in this case, we have ventilation holes along the exterior of our box. We had, go back a little bit, we had a kind of a aesthetic hole for the aperture for the logo on the top of the box, and our connector ports were wide open as well. And so for the ventilation holes, making them smaller is a great way to improve performance, but maybe might affect heat dissipation capability. Maybe that might require another thermal simulation if you want to make many changes to the ventilation strategy. For the connector ports, making the connector ports as small as possible or bonded to the chassis even better makes them less leaky. However, bonding your connector shell to the chassis can increase manufacturing complexity or might even require you to get a more expensive connector with a metallic black shell to even be able to bond to the chassis. That type of connector scheme is really common in FA and D, but as emissions and immunity issues become more and more common for other industries, we're seeing that begin to be implemented in different high-tech applications as well. Finally, the aesthetic design. Are there ways to achieve similar aesthetics without compromising our shielding effectiveness performance? So some of the changes that we made, we have connectors with back shells bonded to the chassis for Ethernet USB-C. And then our floating logo aesthetic was filled, but we also added some new ventilation holes where a fan could potentially be mounted on the roof or the lid of this box. And then we also removed the SD card connector port, so we can make it so like it's on the user of the board to take the SD card in and out if the box is unassembled. So with these updates, this is just the plane wave impinging on the overall box here, just to show a little bit of how we can visualize these results. We see a lot of resonances inside of this box actually. But then looking at the actual updated results, we can see that greatly improved performance to over 10 gigahertz. However, to 10 gigahertz, however, over 10 gigahertz, the wavelengths become much smaller relative to our aperture size and are still able to go through. However, most of our radiated immunity or emissions requirements are up to that 1 to 10 gigahertz range. And so I think this is a great improvement in performance for pretty simple changes here. Next, let's go to just a cable-only simulation. So let's talk about some of the inputs that we can include in our cable simulation. With a multi-conductor transmission line solver, we can have infinitely nested shielded conductors. So many different shields can be included, extremely complex cross sections. The advantage of EMC Plus is that we don't have to mesh the cross section of our cables. We just mesh the routing and then we assign a cross section to it, and the co-simulation with the transmission line solver handles the rest. So some of our inputs that we'll have to add is our cable routing, the cross sections, or terminations. Those terminations might be to extract an open circuit voltage and short circuit current, so we can extract like Thevenin equivalent sources. Maybe some matched loads to reduce reflections, maybe a circuit termination, filters and such. We need to include like electronic box or a simplified board to have a reference for the ends of our cables. We will add current probes and voltage probes to these cables. Then for emissions or immunity, we might add some external field probes. This gives us the ability to probe outside of our computational domain. So imagine we're just simulating a 100 millimeter by 100 millimeter by 100 millimeter box around our enclosure, but our emissions setup is or requirement is trying to get the electric fields 3 meters away. Our external field probe lets us solve just around our smaller computational domain, but then predict the fields at that further point away. We can also add plane wave sources or antenna sources to drive the immunity or susceptibility of our cables. Typically, we will do a plane wave methodology where we drive the simulation with a Gaussian source so we can get broadband results and extract a transfer function. That transfer function kind of equation that we see is on the bottom of this figure, where we take the FFT of our probed results and divide that by the source excitation. So for immunity, this would take the form of we probe the voltage or current on our cable, and then we take the FFT of that and divide that by the FFT of our Gaussian plane wave. And so then we can multiply our transfer function by whatever source we want. We'll be talking about that a little bit more later. As for cable inputs, I have some screenshots of some of the ways that we add information to our cable cross sections in the top right here. That for the top middle, that's just adding our conductor radius and twists per unit length. We add our resistance per unit length, the loss tangent parameters, jacket thickness, and dielectric filler thickness, if that's apparent on a shielded cable, and then transfer inductance. Transfer inductance is a big one here for shields and how we're able to take into account like the complex mechanism that is transfer impedance between shields and interconductors in a pretty elegant way. We have a full library of many different measured shields from that we've measured ourselves or from partner Glenair. Or we have different analytical ways to predict the transfer impedance based on the construction of your shield. And you can, of course, enter in your own transfer impedance values if those are known as well. So for cable-only radiated immunity, just to show like kind of what these results might look like. In this case, I just had, let me go to this board, a two cables going throughout this kind of simplified board representation, and I impinged it with a plane wave, and we can see the fields radiate or cross and scatter our geometry here. And then from here, I measured the short circuit current on a couple of the different cables and extracted the transfer function. Here we can see the results are dB microamps per volt per meter. So that's current per a field at each frequency induced on the cable. And then the same thing for our voltage transfer function. This by itself, you could multiply by what you expect your source to be. Like maybe that'd be 10 volt per meter, and then you'd compare your results with what you like your extracted currents or voltages from what your IC might be rated to handle, or being able to help rate TVS diodes for being able to shunt an overvoltage or something like that. But the magic of simulation here is how we can iterate and see how we're able to just qualitatively improve performance before we're even adding a lot of complexity. So our next step here is adding the enclosure. So here we see the same enclosure that we were simulating at to begin with, but we have the cables that we showed earlier. In this case, it's a low voltage pair, kind of like between a battery pack and connected to the board connector. And then just to show a little bit of complexity on this cable cross section, added a double shielded, twisted shielded pair and two twisted pairs going between these other two connectors. And then again, this is like just a simplified board representation that's really just a reference for this case. And so building off of the inputs that we talked about earlier. The only addition here is the enclosure CAD. So it's really just adding that shielding effectiveness simulation that we ran earlier to this other cable simulation. From here, we can see our radiated immunity results for starting out with the fields scattering and leaking through our apertures into our enclosure. So again, we're impinging the plane wave, Gaussian broadband source. We're extracting the open circuit voltage and short circuit current on some of our cables. And then we're multiplying that transfer function that we extracted by our actual source amplitude that we expect to have in our tests. Like, for example, we'll multiply our transfer function by 10 volt per meter from 30 megahertz to 3 gigahertz for the CISPR radiated susceptibility guidelines. So this is looking at like what the kind of unprocessed results look like. Again, this is a time domain solver, so we just see really when we're impinging it with a Gaussian pulse on the left here, this is just the FFT of the Gaussian pulse, really just looks like noise in the time domain. But then when we post-process this, extract our transfer function, this is when we can see how our performance changes for extracting these the short circuit current. So here we see that very little coupling at low frequencies, but then as we get to higher frequencies, our coupling goes higher and higher. And when we superimpose our shielding effectiveness results on here, we can see that this lines up very well with our expected shielding effectiveness performance. As our shielding effectiveness performance decays, our coupling goes up. But then when we show that our coupling is much worse and much more broadband, I'm just going to go back a few slides, when we don't have our enclosure. This is all as you expect, but when you have an enclosure, your shielding performance is going to go up and your immunity is going to go down, but being able to see how your design changes on just an enclosure level are going to directly affect your overall EMI performance in simulations that take 20 minutes to run is a huge value. And here, same thing, but open circuit voltage. Next, we can talk a little bit about radiated emissions. So here, I took the same model, except I removed the plane wave source and just added a pin voltage excitation on one of the cables. In this case, I just put a Gaussian pulse so that I could get kind of that broadband frequency response, similar to how I was impinging the Gaussian plane wave. But you can add any signal, drive it with your clock signal. Maybe you have a measurement of your, like a current probe on a cable or oscilloscope measurement. We can use that to drive our cables as well. But being able to use Gaussian pulses to extract value means that you're able to run simulations and maybe not be blocked by not knowing what your signal is at the point in time that you're running the simulation. You can make engineering design decisions before you have all of the information for how your platform is going to operate. Beyond that, I added those exterior field probes that I mentioned earlier that are able to probe outside of our computational domain. So before was the results on the exterior of the box, and here we look at the interior. Back this up again. We can see as we start driving the cable on the bottom there, we see reflections going back and forth on that twisted pair, and eventually we see the field leaking out from our hole apertures as well. that's also, you can see that very well in this simulation or this animation as well. Our fields leaking out from our ventilation and our connector holes, the top and sides. And here's just a look at like what our radiated emissions look like at both 100 millimeters away and 1 meter away from the box using the external field probe. Again, just we want to be able to compare these to our simulation iterations to be able to make our design changes. On that note, I think I'll hand it off to Ryan to take on a little bit of information for the PCB assembly only simulations.
Sorry about that. Switching over to my screen. Thanks, Sebastian. So as Sophia said, my name is Ryan. I'm a signal integrity engineer. I specialize in PCB design, especially good design practices to minimize not only signal integrity, but EMI, EMC, ESD, everything else that Sebastian has talked about here. So with this board, we had a couple of weeks where we cracked down and did PCB level simulations of EMC plus. And so we're going to kind of go over some of those results here. Because when you do PCB level simulations and you want to capture all of the interconnects, you have to adjust your mesh size appropriately. So in this first case, what we wanted to look at were if we are driving certain signals on our board, where are the fields located? Are they coupling into any other interconnects in the area, or do they mainly stay in those signal traces? So what we did here was we took a chunk of the board. You can see this is the cutout that we did for this model. We can do, say, this same board with the full model and do the same simulation. It just matters about simulation time. And for something like this, a cutout is perfectly okay. It should capture all of the return currents in that area. So what we see are between the microcontroller and the SD card, we have a bunch of these matched lines. And these are the SD data and clock lines. We can see in KiCad the full routing of these with the microcontroller and that SD. And so we had to mesh this at 0.05 millimeters. That was to resolve the 5 mil traces, which are 0.127 millimeters. And the results we get from this are very interesting, and they're exactly what we would expect to see. So the less sensitive scale on the left, before I play this, this was designed to show all of the coupling paths that the energy in these traces. So with a less sensitive scale here, we see everywhere that the current densities are coupling into. And as we would expect, yes, some of that current density is getting into that chassis connection of that SD shell. Now, this alone doesn't tell you a whole lot because, yes, energy's coupling, well, how much? And that's when we can go to something like a more sensitive scale. And in this animation, we see a lot of that current is located in the traces. This is a probe that's just on the microstrip, so just on the outside traces. But we can see there is a bit of coupling up in this area to the SD shell, but not as much. And we see everything is pretty much localized to these traces and their returns underneath. We do see some crosstalk, which is to be expected, but a simulation like this is perfect to know all of the coupling mechanisms in your system and not just say trace to trace crosstalk. Something else that is very useful in full wave solvers when you have PCBs, you want to get more information out of them, are near field simulations. So for instance, oscillators, clocks with fixed frequencies will often show up on failing EMI, EMC signatures. And so, for instance, in this board, if we were to see this fails at 25 megahertz or any sort of multiple of that, we might start looking at that clock signal and say, what is actually going on as it travels through that board? So what we did here, again, was taking the chunk of the board where that clock signal is routed. It goes from the clock to and through the microcontroller pin out to the Ethernet PHY. So we're driving the oscillator pad here with a clock signal. Again, I put an animated probe on the microstrip traces, and this is kind of just a sanity check. We want to make sure that that current is traveling back and forth. And you can see when this clock signal hits the pin on the LQFP package, that pin is going to have some sort of inductance. And radiated fields, radiation always comes from changing currents. And so the inductance of that pin with the changing current across it is going to create a voltage, and that is going to radiate. So we want to see how bad is that? What is it going to look like? On the left-hand side, we see that animated probe. And again, sanity check. Yes, the current is indeed going back and forth in this, which is exactly what we expect to see. Then again, as expected, that inductance of that pin, when that current hits it, it starts radiating. This is a short simulation due to time constraints. When I originally did this simulation, I didn't have a whole lot of time, but what we should see here as time goes on is this stabilize into some sort of oscillating field that depends not only on the clock source, but any other sort of crosstalk in the area or reflections off the end of your trace. This is another reason why termination is and minimizing reflections is such a big deal in PCB design. So as Sebastian talked about earlier, we also have Charge Plus, which is our FEM solver, and it's great for ESD, as well as like shielding effectiveness, surface charging, all of that. But I primarily use it here for ESD. And so what we've done is, again, taking a small section of the board for basically simulation time. We cut out the section up here where these are the power inputs to the board. You can either power 28 volts here, or you can plug in a USB 5-volt that is regulated down. With any exposed connectors in your designs, they are prone to direct ESD events when someone directly touches it and current flows through it. So what in the EMC Plus model, you see a bunch of different line segments here, and I colored them all a little differently. Your gold segments are just wire connections, where your blue segments are going to be resistors, capacitors, inductors. And we also see a couple of red things. These are switches and a source. This entire thing is your ESD gun. Basically, it charges up a capacitor, and then at a certain time, a switch up here closes, and it allows all of that current to flow in. And for this, we set it up as you would in the lab when you're testing. So we have this nice, huge ground plane, and we have a connection between the board that you're testing and that ground plane. It's about 1 mega ohm. I think it's like 940 kilo ohms. So we set this up exactly as you would set it up in the lab. And a couple of probes were placed on some of the power nets. Because we only had this small section, I looked at some of the power nets to know, okay, we're zapping this shell that is connected to chassis, but it's going to couple into other interconnects in the area. So I'm looking primarily at the power here. And around the USB connector, this red box around it is going to be an animation probe showing the conductivity of the air as we zap it. So first, the really pretty animation. These animations are great also for secondary arcs. So if you had another metal connector in the area and you want to see if I zap the USB-C, is it going to jump across to another connector? You can just make this volumetric probe surround both of those, and you'll be able to tell where arcs can occur. So if we look at this animation, we zap the USB-C at the top center, and we see initially, yes, the field is kind of bouncing around here. The conductivity is bouncing around. And then it settles out and all of the changing fields are coupling much more tightly to that chassis plane that's right underneath of it. So this is perfect, exactly what we expect to see from this simulation. And like I said, the other way we do this a lot is we can do indirect effects as well, which will tell you if you have a ESD source nearby, can it jump gaps into your system and affect anything there? Also placed another surface current probe, and the ESD waveform has basically two peaks. And so initially you see a bit of that energy flow through, and then the sort of lower frequency component mainly stays in the chassis connection. We see it eventually drains out the connection directly to that ground plane here. And then we see some flashing up here. These are capacitors tying together the different ground and power planes. Again, we expect to see that. So this is all really nice. This shows you the direct paths in your board where and how you can damage things. And so viewing animations like this are great for knowing where to add extra TVS diodes or anything to help protect the circuits that need protecting. And again, we did some voltage probes. For instance, that 5-volt power rail coming directly from the USB-C is obviously going to probably be the most tightly coupled interconnect in that area. And indeed, we see quite a lot of voltage, about 250 volts. Now, it's only for a very short period of time. These are 10 to the minus 7 on the x-axis here. So very short pulses, but I mean, long enough to potentially damage any ICs in the area. So what this shows is on my first go through of designing this board, I forgot ESD protection. And so again, the EMC Plus gives us all of this great information to say, all right, anything on that 5-volt rail, we definitely need to add some protection to avoid zapping and roasting all of our components. Something else that is important on PCBs is, there are all of these ways for noise to get into your system. And conducted susceptibility is, any noise that couples onto harnesses. And you figure harnesses can be very long depending on the craft that they're in or the application. Any fields coupling onto those long lines, there's a lot of frequency content there that can be injected into your system. And so here, how we set this up, again, we just took a section of this board. This is the 28-volt input with the kind of switching regulator stuff out here. And we kind of guessed, we took a Gaussian waveform and we said, what if it's, about 100 millivolts? We scaled it to a properly have the sort of frequency content that we expect from that signal. And we basically, with conducted susceptibility, all you're looking to do is there is noise being injected into my system. We are going to measure how much noise that is. And then it's up to the designer to decide, okay, is this noise going to make an impact where we're seeing it. So in the simulation, we have two M harness lines going in 28 volt in the ground, and we injected a common signal across these. And then we just have, again, just a couple of voltage probes. This is going to be located primarily in the input power area. And a couple of plots. So from the about 100 millivolt amplitude common signal we injected, we see what actually gets through to the bus near the switching IC is really only about 4-ish millivolts. So there's a lot of maybe filtering in between where we're injecting that noise and that switch mode power supply. And so again, 4 millivolts, it's kind of up to the designer or the team designing the system to say, is 4 millivolts of common current, common voltage in that area enough to be concerned about? And 4 millivolts, probably not for a lot of designs, but if this were in a sensitive analog area, yeah, you might want to take a look at it and find ways to avoid it. And similarly, the common current through those leads, we see about 900 microamps peak. This is a very, very large common current. Again, this was kind of just a theoretical case. The general rule of thumb, at least for FCC emissions, is a handful of microamps is enough to fail conducted emissions. So I wanted to touch on something else that EMA offers. We've talked a lot about simulations and how we can use our tools to best simulate different areas of your design that you have to care about when you're looking to pass different tests. And while those can give you the most accurate interpretation of what's going on, sometimes it just doesn't fit time and budget, and we recognize that. And so we're proud to offer design review services as well for PCBs. These will have one of our experts looking over the design files for things like signal integrity, power integrity, and EMI, EMC issues. All of the issues that are found are also given recommended fixes, and we try to fit within the bounds of your schedule, right? If you are on your last spin of this board and you can't add in a bunch of filtering, well, we can find maybe some other ways to fix up the design to help minimize any impacts. If requested, this review can also include simulations. These simulations are usually done in a 2.5D solver like SI Wave, or if anyone is familiar with hyperlinks, it's another 2.5D solver. And these will look for things like resonances in your board, power delivery network impedance, which is a huge contributor to failing EMI. And here, a while back, maybe a year now, I designed another board called the Very Bad Board. And this was intentionally drawn very poorly so that I could do kind of an example review of it. And we see the table. This would be in the conclusion part of the deliverable. And you see these issues are ranked by severity. So number one is always stack up. That is a huge area for failing SI and EMC. And then we go down the list. Single exclamation points here. You probably don't have to care about it. If you have time and budget to respin your boards, it's a suggestion. And so, for example, some of the feedback now these were very intentionally designed into my board, but something I see a lot is, for instance, in connectors, bunching together a bunch of signals without thinking about the returns. Those are just as important as those signals. So I pointed out here, this ground is kind of far away. So you're going to see a pretty huge impedance jump going in and out of this connector, and impedance differences with currents generate fields. And again, stack up is something I love talking about. And the original stack up for this design provided very poor power delivery. And the ground and power weren't very tightly coupled, which meant when you're changing layers with your signals, your references are going to be much different. It's just going to be a mess. And so here, I just suggested, hey, change your stack up slightly to this, and you will see much better performance. Did you want to cover closing thoughts?
Yeah, for sure. So overall, just want to really emphasize through this talk that the full platform simulation process is iterative, and you do not have to wait to include all inputs, all components in your simulation to be able to extract value. Of course, more value will be extracted at the end, but doing things as simple as just an enclosure simulation, just adding your cables before adding your PCB with all of the ICs and small components can give you great understanding of how your platform is going to perform from an EMI, EMC perspective. Use of simulation is to reinforce good design practices, not to replace them. If you are going to build up and make sure that you're making those good design practices as you are increasing the complexity of your evaluation, then you are going to reduce the amount of issues throughout your entire design process. And of course, EMC Plus makes the above points easy and efficient to handle, and we have the experts and knowledge to help any of you implement this into your workflows. I think that we have a decent amount of questions that we'll be able to go through for the rest of our time here. Sophia, how do we want to handle the queue here?
Yeah, we can just go down the list. So the first one is the sheet cable simulation inputs. Can you explain more about the option skin depth effect?
The sheet cable, I'll take over screen sharing. Yeah, so in general, we will have the skin depth effect option on here now. This just gives you like that frequency. So we're in transmission line world when we have our in harness cables in our simulation. So it's not solving things in 3D, but of course, very thin sheets of like for a foil shield, or if we have very high frequencies on our conductors, the total energy is going to be kind of exist on the thickness of your actual skin depth. And so skin depth effects just adds you the option to specify your conductivity and thickness. This is actually linked to those other definitions like for a shield or conductor, and be able to include in transmission line world, it actually is a parallel resistance that is frequency dependent. And so we're of course a time domain solver, but we are able to extract the DI dt every mesh cell on your cable harness and take into account the effect of skin depth on the both like the transmission of energy through your cable or like let's say like through a foil shield, for example.
Okay,
But-
oh, go ahead.
Nope. Just my closing thought on that is really the only reason that we specify this specifically is, again, we're in transmission line world. We're not in FDTD full wave world when we are adding these M harness cable parameters.
The second question is, how was the shielding effectiveness of the aperture conceptually simulated?
Yeah, let me get to this picture here. So for these apertures, it really is as simple as we assigned our material and we meshed the thickness of the actual lid here and resolved the apertures in the mesh. So in this case, we actually simulated the enclosure as a body. So we're meshing the actual thickness of the materials. However, depending on the application, that might not be needed, especially things that are hole driven shielding effectiveness, HOLE, like let's say like an automotive platform that has giant apertures for its windows. The shielding effectiveness is going to be dominated by these huge electrically transparent holes. And so we might only have to represent our chassis and overall components of the car as surfaces. Sometimes for longer holes, like relative to the, like if like let's say like the aperture aspect ratio of the hole size versus the depth size, when they get longer relative to when the aspect ratio is bigger relative to like the whole length versus the whole area, then that's when they start acting kind of wave guidey, and we have to actually mesh the overall dimensions of the hole. But when we have a larger aspect ratio, so the whole area is much bigger than the whole thickness, then we can represent this as surfaces. But in this case, it was very easy to mesh this with a 0.5 millimeter mesh and resolve both the thickness of the holes and the area. So I did. It really, we have a lot of different tips and tricks to really just make simulation time faster, easier to deal with. And in this case, 20 minutes was something that was easy for me to deal with on my desktop. If I was really worried about it, I could send it to my HPC, and I ran the same simulation in 3 minutes on an HPC. And when I start getting past that limit of like, okay, I need to make my computational domain more efficient, that's when I start implementing these tricks. But for a lot of simulations, EMC Plus, the FDTD solver, and the transmission line solver are very scalable, even on hardware resources for like a laptop. And so I'm able to mesh and resolve them explicitly.
And the third question is, missed the influence of the thickness material and the skin effect during the explanation of the model. Can you explain this?
So I'm not sure if that was the in regard to the cables or not. I think we talked about the cables enough, but on that point, let's just talk about the expand what I was going on about meshing in a body versus surface. And so one, for skin depth effects, for shielding effectiveness anyway, the performance of an enclosure is going to depend on the type of enclosure. So for I guess I'd say consumer electronics or a high-tech industry, your shielding effectiveness of enclosures is generally dominated by holes, the hole aperture, like in this example, HOLE. But then when we get into something that is more shielded, where we have like specific like EMI or filters or ventilation that is EMI protected, and we have no specific holes, then our shielding effectiveness is driven by seam apertures, like where, let's say, like two panels of metal come together, or if it's a composite hybrid enclosure, then maybe your conductivities are low enough that the transmission through the actual walls of the material might start dominating your shielding effectiveness effect. And so that gets into, if we are expecting the transmission through the a wall to significantly dominate our shielding effectiveness result, then we need to explicitly resolve the mesh of that wall thickness and have like at least 2 mesh cells in the thickness, probably more than that, depending on how small your skin depth is relative to your wall thickness. And that's when we usually wouldn't be able to use a surface representation. That did change a little bit in the 25 R1 release, and we added a new multi-thin layer tool so we can have a surface definition, but we assign it like different dielectric coatings or like radome materials, and it's able to handle the skin depth transmission or scattering off of that material really well, even if it is a surface definition. But in like fundamental FDTD, before that kind of application was developed, to properly take into account skin depth effects, you had to actually have good mesh resolution through that thickness. But we recognized that causes your computational domain to blow up in size. And so 25R1, we released the new multi-thin layer tool. It's kind of a roundabout answer. I commented on quite a few things, but overall, depends on the application, on if skin depth effects is actually matters or not. And we have ways to efficiently tackle it if it does.
Great. Thank you, Ryan and Sebastian. It's time to conclude this session. As a reminder, any questions we did not answer today will be addressed via email. Following today's webinar, all registrants will receive an email from EMA with a link to the recording of this presentation. If you have questions about a particular section of interest to you, please feel free to reach out either through the ema3d.com website or email. Thank you all for your time and attention, and have a great rest of your day.